So at this point, I made a list of things to talk about in the air. It's not ideal. But anyway, so apparently I have instructions which I haven't looked at yet. Apparently I can tell at what time each person joins the meeting and at what point they leave the meeting. As I said last Thursday, I take attendance and I'm aware of it, but don't use it directly, and not against you. I mean, I think you should attend class. I think you should attend all your classes. But if you don't, but I do keep a record. And if there's ever any reason to bring it up and someone like has a perfect attendance record, I'd say, oh, this person, is very conscientious and meets their obligations and so on. So that's the only way in which I would use it, other than obsessively keeping records for the sake of keeping records like that. So with your kind permission, or without it for that matter, let me say something about the general nature of mathematics. So in mathematics, we choose a starting point. And of course, we emphasized this in geometry last term. But the idea is, in all of mathematics, you choose a certain set of initial statements. And we're not making any statement about whether they're, quote, true or false. And by the way, when I'm talking, there is a way in which you can raise your hand, but for the moment, let's see how this works. Just unmute yourself if you have a question or want to say anything. This really is not satisfactory. And the class is just a live give and take. It's much more natural. It's dynamic. I can see everyone all together here. I can't see you all together. So if you have something to say or a question, or if you want clarification, or if you have a complaint, actually, we're not accepting complaints today. The complaint department, the dissatisfied customers complaint department is closed. No, seriously, if you want to say anything, please do. So what we do is we take some starting points, and the only requirement for these starting points, they're called axioms or postulates, is that they be meaningful. They have to make sense. Can't just be gibberish. It doesn't say anything, and they have to be consistent. We say a system is consistent if there are no two statements of the form P for proposition. P is often used, P and Q. You've done this in truth tables probably. P and not P. That constitutes a contradiction, and it's not too difficult to prove using truth tables, very elementary truth tables that you don't even really need truth tables. You just have to know the truth values of and or. You can prove that if you have one contradiction, even the tiniest little, most obscure contradiction in a tiny hidden corner of a mathematical or logical system, then every statement is true and every statement is also false. So 2 + 3 = 5, 2 + 3 doesn't equal 5, 2 + 3 = 10. All those statements are both true and false, so everything falls apart. And so you can't permit contradictions. However, the issue, I was just talking with John before, we talked about this a little bit last time, the issue of consistency and verification that there are no contradictions in the system turns out to be a very recondite, very, very difficult, obscure matter. But once you've concluded a certain set of axioms or postulates, the only question you have in mathematics is where do you go from there? So, what can you deduce by a sequence of logical steps? And speaking of logical steps, let me mention 2 things about logic, which I believe I'm pretty sure I mentioned last term. I try to mention it in every class. First of all, in mathematics, we use the word logic in a much more formal and specific sense than in ordinary parlance. I think the example I gave was something like this. People might say, well, if they're predicting rain, the logical thing to do is have an umbrella with you. That just means it's a reasonable thing to do. that's not how we use logic in mathematics. In mathematics, we use logic in a very precise way. It's made particularly precise in truth tables. But basically what it means is something follows from something else in an incontrovertible, not to use the word I'm defining, but logical way. It's a necessary consequence. That's what logic means in mathematics. The other thing is, when we speak of two statements as being logically equivalent in mathematics, we mean that starting with either one, together with all the other known facts in the system, the known facts being axioms and things that you prove from axioms called theorems, as you know. So two statements, say P and Q, are logically equivalent, or just equivalent, because in mathematics, you can define equivalent to be anything you want. Equivalent sets are sets with the same number of elements. You could say two sentences are equivalent if they have the same number of letters, but in English say, but that's silly. So in mathematics, when we say logical, two statements are equivalent, we mean logically equivalent, and that means, as I was starting to say, assuming either one, you can establish, you can prove the other one along with everything else you know. So, for instance, in geometry, in Euclidean geometry, two statements that are logically equivalent are: if three sides of a triangle are congruent, have the same length, then the three angles of the triangle are also congruent, have the same measure, the same number of degrees. And conversely, if you have a triangle, Euclidean triangle, with three congruent, equal in measure angles, then the sides have to be the same. Or to put it more succinctly using definitions, if a triangle is equilateral sides, then it's equiangular angles, of course. And conversely, if it's equiangular, it's equilateral. So basically, two statements are logically equivalent if it and its converse are true. So where are we going to start in the theory of numbers? Well, because we want to concentrate on the characteristics and the behavior of numbers and what the set of integers, whole numbers, is like, we're going to start with a certain set of initial statements called axioms for the integers that will be totally familiar. They've been familiar, maybe not with the words, but since elementary school, most of them. So that will be no problem. And they'll be so familiar to you, and you've had so much experience with them that you'll readily accept them. And then we will go from there and see what properties the integers have on the basis of those axioms. Having said that, let me remark, for your edification, that it's possible, first of all, to predicate all parts of mathematics on the basis of formal logic. In mathematics, we generally use Aristotelian logic. Aristotelian, an adjective of Aristotle, which in particular has the law of the excluded middle, which means a statement is either true or false, and there's no middle ground. Statement isn't partly true or partly false in mathematics, and that's not true in life. In life, there are gradations. Something is definitely true, possibly true, probably true, maybe true, possibly false, likely to be false. You have all these gradations, and there is a part of mathematics called fuzzy logic, fuzzy, not sharp logic, which is actually used in television communication and elsewhere. So there are actually uses of fuzzy logic, but in regular mathematics, the statement is true or false. It's not both, it's not neither. So we could, but we're not going to. This would be maybe in a class called something like Fundamental Concepts of Modern Mathematics, where you would actually start developing the number system from set theory. And there, of course, is called set theory and logic. And you actually build up the number system. Next time in abstract algebra, we will take an approach something like that. There'll be some overlap between number theory and abstract algebra because a ring is RING, ring, it's called a ring, is a generalization of the integers. So historically, that's what it emerged from. But there will be some overlap between what we do this time and if you're in the class in abstract algebra, which I believe is 4010 next term, so it's close to 4200 like this. But we'll do it from an algebraic point of view. And there we will, as I say, actually build up the integers and see where they come from. And on the basis of that, we will build up a set of rational numbers, fractions whose numerators and denominators are integers, the denominator not zero, and the complex numbers. And we'll do that axiomatically. So you see what these other kinds of numbers, what the integers are, the rational numbers, and the complex numbers are. And in Mathematics 4010, you see what the real numbers are. Basically spend most of the term studying the properties of the real numbers. So here we go. I hope you can write this down. If not, it'll be recorded. And again, by Thursday, presumably, I'll be able to write notes for you. I'll have to learn how to do that and learn how to send them to you, but we'll do that maybe. So let's take a look at some of the properties that we will be, I don't want to say assuming because you've been taught not to use the word assume in mathematics, but that we will be basing our further work on. So first, we'll start with 5 properties of addition. So the first property of addition is, I think I mentioned last Thursday that we use a fancy capital Z. Yeah, I did. From the German word for number to represent the set of integers, the integers being the positive, negative, and 0 integers, the natural numbers being the numbers that naturally occur in life, 1, 2, 3, 4. The natural numbers, as I think I mentioned Thursday, some formulations, when you build up the natural numbers on the basis of set theory, you define 0 to be the empty set, and then 1 is that 0 together with the set containing 0. Anyway, it builds up what's called a successor set. So when you do that, when you use that formulation, 0 is considered a natural number. It's not a big deal, but in general, I won't. But there's an obvious one-to-one correspondence, a perfect pairing, a one-to-one correspondence, perfect pairing, the holding hands, between the natural numbers and the positive integers, obviously. The natural numbers are unsigned. They don't have signs. They're just 1, 2, 3, 4, the counting numbers. And if you say there are 2 people standing there, you don't say there are positive 2 people standing there. You say there are 2 people standing there. So the natural numbers are unsigned. The integers are signed. Oh, I forgot to bring the clock. Someone will have to act as timekeeper. So there's a clear, simple one-to-one correspondence. The natural number 1 corresponds to the integer positive 1. Natural number n corresponds to the integer positive n, and so on. So first of all, we have the law of closure for addition. So the first 5 properties, as I said, refer to addition. So the law of closure, so it's closed. The law of closure for addition says that when, I think, for some of you this will be familiar, but even if it is, the review doesn't hurt. And things have a way of starting out simply in mathematics and becoming, kind of difficult and complex. So indulge me in what may be a repetition at the moment. So, okay, the first property is the property of closure. It says that if a and b are integers, then a plus b is again an integer. Okay, so the set of integers is closed. You don't jump outside it to get a result. It's often useful to look at a counterexample. A counterexample, as I hope you know, is an example to show that something isn't true. I may even have mentioned that on Thursday. So a counterexample to closure is, for instance, if you consider just the set of negative numbers or negative integers, when you add 2 of them, you stay in the set of negative integers, but when you multiply 2 of them, as you know, and as we may prove this term, definitely prove next term, when you multiply 2 negative numbers, you jump outside the set of negative integers. And so we say the set of negative integers is not closed under under multiplication, but it is under subtraction. What do you think about the set of rational numbers? Is a set of rational numbers closed under multiplication?
Yes.
Yes, okay, I agree. Is the set, well, what about that? Is a set of non-zero rational numbers closed under division? Go back to the fourth grade, you invert the second fraction and multiply numerators and multiply denominators. And since I've excluded the zero rational number, we're not going to have a problem with when you invert the zero in the denominator. So what do you think about that? When you multiply, when you divide two rational numbers, you can try it, you probably get a rational number. But what happens when you divide two integers?
What integers?
You divide two integers that you can divide, which doesn't include zero. Again, it's not difficult. I think I won't do it unless you want, but I'd have to write it down. It's not all that difficult to prove that if you permit division by zero, then everything is, all number combinations are true and false. You know, like 2 plus 3 and so on. An easy way to see that without going through the whole proof is observe, do you agree that 0 times 1 equals 0 times 2? That requires proof. Do it next term, maybe even do it this term. Yeah, when you multiply by 0, you get 0. That leads to places. That leads to the whole theory of ideals. I'm mentioning these things because some of you want to go on mathematics. And even if I'm not covering something this term, if I think of something that you may see in the future, I'll mention it because having heard it once before, I make it seem less alien when you hear it again. So that leads to, invented by Gauss, the theory of ideals, the idea that when you multiply by 0, it pulls you in. Okay, I won't go further with ideals now, but it's interesting. So okay, so yeah, 0 times 1 equals 0 times 2. Well, if you could divide by 0, divide both sides by 0. If you like cancel the zeros, and you're left with what? 1 equals 2. And of course, you can do that for any number. So any two numbers are equal to each other. So again, the whole system of arithmetic breaks down. Okay, so that's what closure under addition means. It means when you add two integers, you again get an integer, you don't get something else. So A plus B is an element of, you know, the symbol for it is an element of. Let's see if I do it that way. Is it? Yeah, I think it'll look right for you. Yeah, because it's backwards for me. You know, the symbol for is an element of. So you could say A plus B is an element of. It sort of looks like a backwards E with a curved side, is an element of Z, the fancy Z. It's a Z with, well, I'll write it for you by hopefully Thursday. Next, addition is a binary operation, which means, okay, you're excused. A binary operation is, again, we'll make this more precise, but for our purposes, a binary operation is something you do with two numbers at a time. Again, in abstract algebra, they don't have to be numbers, but for us, it's two numbers. So for instance, if you were adding 2 plus 3 plus 4, that's redundant. I said adding and then I said plus. If you're adding 2, 3, and 4, which is not redundant, you are so smart, you'll probably get the answer very quickly. But in fact, if you think about it, addition is defined on only two numbers at a time. So what you are doing and what the fastest computer is doing is still adding two numbers at a time. So if you have 2 plus 3 plus 4, first you have to execute the 2 plus 3, and then you take that result and add 4. And if you think about that, what do you get? 2 plus 9, do you get? Is that right? 2 plus 3 plus 4? Yeah. But another way to do that, so there you're grouping the 2 plus 3 you're getting that result and then adding the third number. But what if you shift the parentheses over, and instead of catching the first two numbers in parentheses, associating the first two numbers, you shift the parentheses over and you put together, you associate the second two. No, I don't have any numbers, any notes. The second two, no. What I could do is, I guess, make another recording of this, leave it not on, or what I could do is what I did last term, write out the notes and then take a picture of them and send them to you on Blackboard. I could do that. But anyway, let's continue. Can I share the screen? I don't know what that means. I see everyone. So the fact that those, it's the green button. Oh, okay, I can do that. I don't know what that will do, but I saw, yeah, that green thing up there. If this decides to stay down.
Yeah, once you press that, your camera disappears.
Once I do that, what?
You just turn on and turn off your camera. Now it's on again.
Well, the first thing says screen. What will that do?
So you want to share your screen? That's what you want to do?
No, I don't know whether I want to do it. I don't even know what it means to share a screen.
If you share the screen, you can see, we can see your computer screen.
No, yes. So the share
yeah.
The screen, the screen will be like if you're using the Word, if you're on the Chrome, on the Google Chrome, on your navigator, but we are actually seeing your camera.
Listen, I don't know what navigator means. I don't know what Google Chrome means. Furthermore, I don't have that Apple Pencil that would allow me to write on the screen. So for that, we'll have to wait till Thursday, and then we'll try this again. But for now, I'm just going to continue talking. I see you, and you have the misfortune to see me, I suppose. So as you know, parentheses, or in general, symbols of inclusion, which are curved parentheses, square brackets, braces that you use for sets, angle brackets that look like that. Those are all symbols of inclusion. We'll just usually use parentheses, and that means you execute the operations indicated within the parentheses first. So one way to add A and B and C would be to take A plus B, parentheses, plus C, see what you get from A plus B, and then add C. Another way to do it is to shift the parentheses over, leave the A for the moment, and then leave the A plus, and then just catch the B plus C, do the B plus C first, and now you have A plus the result that you got from B plus C. And the remarkable thing about that is that those results are equal. So that's called the associative property of addition. And what it says is that if you have open parentheses, A plus B, close parentheses, plus C equals A plus, open parentheses, B plus C, close parentheses. That is a statement of the associative property, and that holds for all integers. As you know, for other sets of numbers as well, but we're not dealing with those here. I should mention that the reason we give names to things is that they are not universal. Things that are universal, you don't have names for. A name distinguishes something or separates it from other things. So an example I've given, for instance, is with people, you have categories by age of newborn, infant, baby, child, teenager, adult, elderly, and so on. But we don't have a separate name for all people who are under 300 years of age, because everyone is, at least so far. So we institute terminology or nomenclature when something isn't universal. If it's universal, then, well, for instance, closure. If all systems were closed, we wouldn't have to distinguish it with a separate word. That would just be a property of everything. So in fact, there are non-associative algebras. Okay, next property, property 3. This is the usual order. There's no real canonical order. Canonical means standard, but you usually do the next one. Property 3 is there is a particular distinguished number, which we call 0, and write as a sort of vertical circle, as opposed to the English letter O, which is more circular, that it has the property that if you add it on either side to any integer, you're left with an identical integer. In other words, we have this special integer, I called it distinguished because it's distinguished, it's separate, called 0, that has this property. If a is any integer, then a plus 0 equals 0 plus a equals a. And I put that in because it has to work on both sides, first or second. So a plus 0 equals 0 plus a, which equals a. And so, as you know, 0. Someone please mute yourself, although I think I can mute everyone. Just unmute yourself if you have anything to say. Anyway, so since 0 upon addition leaves what you started with, you get an identical result. It's called, as you know, the additive identity. I just said the additive identity, not really justified in positing its uniqueness. The is the definite article. It means there's only one. Without a little proof of that, we don't know. Maybe there's another additive identity. Don't look too hard. You probably won't find one because it is unique. Unique means it's just one. So I'll say 0 is the additive identity, but it's not really justified. Maybe I should say an additive identity until we prove that it's unique. But I'll go ahead and say B. Property 4 reverses. If you think of 0 as a starting point, and now you take the integer, say a, can you get, so to speak, back to the identity? And you can, because we will posit the existence of an additive inverse. It's called an additive inverse for each integer, which means that if you take any integer and you add a certain integer, you'll get, quote, back to 0. You're not really going back and forth. You get 0. But if you want to think of it as going back to 0, for instance, if you think of the number line, and here's the number a, and here's the number 0, there's a number which we call negative a, or the additive inverse of a, that takes you back to 0. And the additive inverse of a is denoted, as you know, with a horizontal dash to its left. And so we read that as negative a. Some people erroneously read it as minus a. It's negative a. Minus is a binary operation which only operates between two numbers. So that's an operation. A negative sign is a sign of direction, positive or negative. And property 5 for addition is called the commutative, not communicative, but commutative property of addition. And what does commute mean? If you commute to work or school, what do? You don't just go, you go back and forth, right? Commute means go back and forth. So the commutative property of addition says that the order in which you add two numbers is immaterial, it makes no difference. In other words, a plus b equals b plus a. So here's a, and you can take a plus b, or you can take b plus a. So the b commutes with a. Again, not all. Can I slowly list all the properties? Why don't I actually list them on Thursday without this discussion? I'm discussing it now. I'll just list them on Thursday. So again, we wouldn't have a special word like commutative if all systems were commutative, but I think many of you, especially if you took Mathematics 4100, linear algebra, know of a system, a very prominent and important system that is not commutative under a certain operation. What am I talking about?
Matrix multiplication.
Matrix multiplication. So if you know what that means, you probably should, at least at some level, how to multiply two, say two by two matrices in general, they don't commute. Okay, so we have those 5 properties of addition. And as you know, we have another binary operation called multiplication. And that's the word. It's multiplication, or as a verb, multiply. I guess you don't do this, but you'll sometimes hear elementary school students say, you times 3 by 4. No, you don't. You multiply 3 by 4. And the name of the operation that you indicate by putting it between the two numbers is called times. So it's 3 times 4. And when you take 3 times 4, you're multiplying, not timesing the numbers. It's just like subtraction and minus. 10 minus 2, but you're subtracting 2 from 10. Or plus and addition. So here we go for multiplication, and multiplication is also commutative. So commutative property of multiplication. Well, before we do that, multiplication is closed. So the closure property for multiplication. Closure property for multiplication says if you multiply 2 integers, you get an integer. Unlike when you divide 2 integers, it's not closed. 3 divided by 4 is not an integer. But multiplication of integers is closed. So if A and B are integers, so A comma B element of Z, then A times B is an element of Z. And as you know, there are different ways of indicating multiplication. If you're dealing with numbers, like in elementary school, you sometimes use an X between the numbers. And you still sometimes do that, for instance, with matrices, a 2 by 3 matrix, you'll often indicate 2x3. But in working with especially algebraic symbols, it's better to avoid using the X for multiplication, even though the X, if you take a look at printed mathematics, letters that stand for numbers are always indicated in italics. So in print, the number X looks different from this symbol X, which is a plain cross like that. So it's better to either use a dot between 2 numbers that you're multiplying, and if they're numerical numbers, you need a dot. For instance, if you write 2, 3 juxtaposed, put next to each other, it's not 2 times 3, it's 23. So you need a dot. And be careful with penmanship. Make sure if you mean 2 times 3, the dot is in the middle of the numbers, because if you put it on the bottom, it's not multiplication, it's a decimal point, 2 3/10. So you have to write carefully. As you know, another way of indicating multiplication is with parentheses. So you can put parentheses around the A, and parentheses around the B, or parentheses around just one of them. You can use plain juxtaposition without, putting next to each other, without parentheses. If you are using literal numbers, literal is Old English for letter, and a literal number is a letter that stands for a number. So for instance, if you write AB, it means A times B. You don't have to use a dot, you can. You don't have to use parentheses, you can. Ordinarily, it's easier not to. And you can also do it with a numerical number, an actual number, and a literal number. So for instance, if you write 2x, that indicates multiplication. So anyway, we're up to closure of the integers on the multiplication. You multiply 2 integers, you get an integer, you don't get something else, like a fraction. Now we'll take a look at the associative property for multiplication, which is analogous to the associative property for addition. Namely, if you have 3 numbers that you're multiplying, keeping the same order, and that's important, the order is the same, but the association, the position of the parentheses is altered. So you just shift the parentheses over and you reassociate. Associate means put together the second 2 numbers instead of the first 2. So the associative property of multiplication is parenthesis, open parentheses, A times B, which you can write as AB or A dot B in the middle, not at the bottom, close parentheses, C equals A open parentheses, B times C, close parentheses. Because again, multiplication is a binary operation. You can do only 2 at a time. Even a computer does it fast, but it's still doing 2 at a time. But you keep the same order. I'll get back to the order presently meaning shortly. Okay, so far we have two, this is so unsatisfactory. I wish I could see all of you live, and if you raise your hand, I could easily see you, and you wouldn't be hesitant to say something. I could move this over and see other people. Oh, there's Lily. But this really doesn't duplicate being in a live classroom.
Dr. Friedland?
We're doing our best, but
what's the difference between a closure property and field? Does field is closure and more, or are they one and the same?
Wait, sorry, closure, and what was the other one?
Field.
Field?
Properties of the field.
Yes. F-I-E-L-D, field?
Yes, sir.
Take Math 4010 next time and you'll see. I mentioned the ring before. A field is another one of these structures of abstract algebra. And what you do in abstract algebra is you take out the properties that are already familiar to you from a concrete example, such as this term in number theory, and you say, okay, what are the essential properties of this system? You know, what's going on? Notice that I mentioned multiplication by 0 before. Notice that when you multiply an integer by 0, you get 0. Notice that when you multiply a rational number by 0, you get 0. Notice that when you multiply a real number by 0, you get 0. Notice that when you multiply a complex number by 0, you get 0. Notice that when you multiply a matrix by the additive identity, it's not the number 0, it's a matrix with all zeros in it. If you multiply the 0 matrix with all zeros by a matrix that's, of course, multiplicatively conformable to it, has a proper dimensions, you get the 0 matrix. So, like, what's going on here? Is this all an accident? Is this, are these things you just have to learn separately? Oh, in this system, we have this, in this system. You start to think, maybe there's something in the structure, in the underlying construction of the system that leads to all these, and that's the subject of abstract algebra. And so you take a look, instead of studying specific, I'll say, numbers or elements of any set, you study the underlying structure. So you abstract, you take out the essential properties and you study them. So a field is a structure that we have in abstract algebra. You actually know some examples of fields. The set of rational numbers forms a field, the set of real numbers forms a field, the set of complex numbers forms a field. We'll go into that more next term. So far we have two non-interact, what time is it? So far we have two.
Just before we go on, we are going to get a set of notes for this lecture, correct, sir?
You'll be lucky to see me again if I can get onto Zoom again.
Fair enough.
But if I can, yes.
Thank you.
Thank you. Okay. Thank you for your approval of getting a set of notes. Okay, but look, so far, this discussion is okay. It's not ideal, but somehow we're chatting about it. So far, we have two binary operations, but they're non-interacting. They don't interact. They don't know each other. Well, there is a property that involves both of them and unites both of them. And that property, as I trust you know, even if you don't remember the name, is anyone know? What property of numbers, what basic property of numbers involves both multiplication and addition?
Distributive property.
Yeah, the distributive property. So here we have the distributive property of the integers, and it says, so you know what distribute means. It means, if I distribute papers to each of you, which I could do in a real class, but not here, that means what? I'm giving it out to each of you. You get it, you get it, you get it, and so on. So the distributive property of it's really, the whole name is the distributive property of multiplication over addition. Multiplication over addition. And what it says is that if A, B, and C, so now we're again working with three numbers, if A, B, and C are integers, then the number A times, open parentheses, Now we're going to have addition B plus C, close parentheses. And now separate from that, so there the parentheses indicate that you do the addition first, right? So you're holding the A in abeyance, you're doing the B plus C because they're in parentheses, and you're going to take A times what you got from the B plus C. And another way to do that would be to distribute that multiplier A over each of the terms. Terms are things separated by pluses and minuses, each of the terms in parentheses. And so this time we're going to do the multiplication first. We're going to take A times B, which you can write as AB, plus AC. And so there, observing what's often called the order of operations. What does the order of operations say? When you have a competition between, oh, yeah, like that. Did you see that when someone posts a black, so you saw that? Yeah, that's what it says. I should get one of you to write it and post it since I can't. So the order of operations says when you have competition between collective notes, okay. When you have competition between addition and multiplication, addition or division, multiplication or division, and addition or subtraction, unless parentheses indicate otherwise, you do the multiplication and division first, and then you do the addition and subtraction. The point of the order of operations is to avoid the complexity of having nested one side another, nested parentheses. Although if you have one set of parentheses, you need parentheses inside that. Sometimes it's easier to read if you write the interior parentheses, symbols of inclusion as brackets that I mentioned before. Anyway, so that's what the order of operations is for. I mean, you could put parentheses around the AB and the AC, but dropping the unnecessary, the superfluous parentheses, if we write AB plus AC, we'll understand that means you do the multiplication first. And what the distributive property says is that those two formulations, those two ways of writing that example, that numerical example, are equal. So what the distributive property says is that A times B plus C in parentheses is equal to AB, that done, plus AC, that done, and then you do the addition. So in the first one, you're doing the addition first, and the second one, you're doing the multiplication first, because you're distributing the outside multiplier, the A. And again, you might say it's remarkable that both of those two very different ways of doing the arithmetic turn out to be equal. So to adumbrate, that means to foreshadow abstract algebra, I'll just mention that the first four properties for addition say that addition forms what's called a group, an additive group. If you throw in the fifth property of commutativity, it's called a commutative group or an abelian group, after the Norwegian mathematician Abel, A-B-E-L. That's not part of this term's work. We'll do that next time. And if you bring it up to the point that we have now, we have those 8 properties, 5 for addition, 2 purely for multiplication, closure and associativity, and the one that connects both of them. Then we have what we'll call next term, and I used the word before, a ring, R-I-N-G. Once you have a ring, there are some optional properties, and one optional property is that is something that's analogous to the third property in addition, namely, in addition, we had the existence of an additive identity. In a ring, we can have, and in the integers we do have, a multiplicative identity, which under multiplication leaves any number identical, and that number would be, if you followed that long introduction, that number would be what? That number, which is the multiplicative identity, which leaves any number identical when you multiply it by that special number. Of course, it's 1. So The ninth property is the existence of a and again, I'm saying a multiplicative identity because we haven't proven uniqueness, but yeah, there's only one number one that does that. So the existence of a multiplicative identity, 1, that has the property 1 times a, where a is any number, equals a times 1. Not all systems are commutative, so you have to say that. A times 1 equals 1 times a, which is a itself. I'm being very fussy about the idea that the identity has to work on both sides because I remember I had a question on my abstract algebra test once, and it was a true or false question. And the statement was 0 is the additive identity. And I thought, there's a trick question here, but I couldn't figure out what the trick was. I figured, okay, any number plus a equals that number. So yeah, a is the additive identity. But, oh, sorry, the question was the identity for subtraction. That was it, the identity for subtraction. So I thought, okay, a minus 0, that's a, isn't it? Yeah, I decided it was a. I knew there had to be something wrong with that. And what was wrong with it? So I said true, but you see why it was false, right? It doesn't work on both sides. 0 is not the identity for subtraction because although it's true that a minus 0 equals a, it's not true that it works on the other side, that 0 minus a equals a, actually equals negative a, which, as I said before, should be called negative a rather than minus a. Okay, so we have a multiplicative identity. We also, another familiar and important property of multiplication of numbers is that it's commutative. Unlike matrix multiplication, unlike subtraction, subtraction is not commutative. A minus b does not equal b minus a, unless the numbers are the same, in which case they're both 0. But multiplication is. So commutative property of multiplication, a times b equals b times a. And again, that's not necessarily so obvious, and you might say it's a remarkable property. It's remarkable that 3 times 4 equals 4 times 3. It's remarkable in a certain sense that 3 sets of 4 is the same as 4 sets of 3. Those are different statements, but they're equal. And now, if you threw in to, that's sometimes called a skew field, if you threw in, which we're not going to, the existence of multiplicative inverses for non-zero numbers, you would get what's called a field. Okay, we won't do that. Leave that to Mathematics 4010. Okay, we also have certain other characteristics of the integers. I mentioned the absolute value on Thursday. Oh, we have another student in the class. Very good. Oh, you can't all see that, can you? How can I make everyone see the cat there? Can I do that? Oh, well, we have a cat present with us, which is very good. Last term, some of you may remember that Arunima brought her a pet dog to our geometry class. Okay, hey, listen, anyone who's willing to listen to this, I'll take. Okay, so the absolute value of a number indicated with a pair of vertical bars is the cat is being duly petted by, yeah, I guess, yes. Someone said you should pet the cat, that's appropriate. So the absolute value of a number, so you can indicate that or define it 2 ways. Sort of the more intuitive way is to say that the absolute value of a, so you put an a in there, is, and then there are 2 possibilities. It's a itself, is if a is already greater than or equal to 0, which means positive, and you want to make it positive. So if a is negative, then it's the negative of a, because as we'll show carefully next term, the negative of a negative is the positive. Some of you may know another way of indicating or of defining absolute value. Anyone know? You can define the absolute value more succinctly as the square root of what? Of the square of A. So the absolute value of A is the square root of A squared. Why does that give you absolute value, which is non-negative? It's because when you write the square root sign, well, listen to this. It's called the radical sign. It's called the radical sign, but the number that you're applying the radical sign to is called the square root. Yeah, the square root of A squared in parentheses. Is called like the square root of 2 or the square root of A. It's not radical 2. It's not radical A. Even some of my colleagues read the square root of 2 as radical 2. No, it's not radical 2 because then the cube root of 2 is radical 2 and the 50th root of 2 is radical 2. So it's a square root of 2. It's a cube root of 2. Say what you mean. It's written with a radical sign, but the number is called the square root, the cube root, the fourth root of whatever the number is. And the reason for that is you are perfectly well aware of the convention that if you write a number and it doesn't have a prefix sign assigned to its left, it's understood to be the positive of the number. So if I write the number 4, it's positive 4. And similarly, if I write the square root of 2, it's the principal of positive square root. So the absolute value of A is the square root of A squared in parentheses, which is, let's say, greater than 0. I would say greater than or equal to 0. So absolute value is non-negative. You know the distinction between non-negative and positive? Positive means BRB.
Be right back.
Be right back.
Oh, okay. I don't know these codes. The difference between, and you've certainly encountered this if you've taken advanced calculus or whatever they call it now, fundamental analysis. The difference between non-negative and positive. Positive means strictly positive. And by what's called the Trichotomy Law, trichotomy, C-H-O-T-O-M-Y, trichotomy, cut into 3. The Trichotomy Law says that every number is exactly one of the following. It's either positive or the additive inverses of the positive numbers are called the negative numbers, or 0. That's in a category by itself. Just as any other number that's not prefixed by a positive sign, by a negative sign, it's understood to be positive. Again, the same with the square root. It's sometimes called the principal square root. It means the positive square root, positive or 0. So non-negative means it's not negative, and 0 is not negative. It's also not positive. So 0 is neither positive nor negative. So when you say non-negative, you just mean it's not negative, but that admits the possibility of 0. By the way, although we haven't formally defined even and odd yet, so 0 is neither positive nor negative. Is it even or odd or both or neither? What do you think about that? We mentioned it on, Duncan already said so. Yeah, we mentioned that 0, and actually in the decimal system, the number that ends in 0 is even. All right, so we have the absolute value, which we'll have occasion to look at, but it's actually more important in analysis and in real numbers. Let's also take a look at some, I hope it's taking a look at the time, which I'm not. 7:02, okay. We started 5 minutes late, but let's see if we can end in 3 minutes. Let's talk about greater than size. So numbers have size, and some numbers are bigger and some numbers are smaller than others. And we formalize that in the definition of greater than, more than, bigger than, and less than. So if someone shows the symbol for A is greater than 0, sure you can do that. I'm sure you all know it, but okay, so that says A is greater than 0. It's bigger than 0. So notice the wider part of the, how should I show this? Yeah, no, this way. So the wider part is adjacent to or next to the bigger number, and the narrower or smaller part is adjacent to the smaller one. So we can turn that around, and if A is greater than B, that also means that B is smaller than or less than A, and so we turn around the greater than sign and make it into a less than sign. So, so you can post. Okay, so the first one says A is bigger than B, and the second one says B is less than 0, and that would be another way of saying B is negative. That actually requires a little proof, but we'll assume that greater than means positive and less than means negative. You can actually prove that. Maybe we'll do it later. If not, we will next term. And as you know, you can also form a compound symbol greater than or equal to, or less than or equal to. So that includes equality. So what's the definition of A is greater than B? And that's the same definition as B is less than A. Those two statements are synonymous. If 4 is bigger than 3, then 3 is less than 4. So when you have one, you have the other. And so let's take this definition of A is greater than B. We'll say A is greater than B if A minus B is positive. So for instance, 10 is bigger than 8 because 10 minus 8 is the positive number 4. So again, A is greater than B means explicitly A minus B is positive. So we're defining this new term, which I know isn't new for most or all of you, in terms of the fundamental binary operations. So A is greater than B if A minus B, and that A minus B is actually the definition. So it's not necessary to say if and only if. In a definition, we don't need if and only if. So A is greater than B by definition if A minus B is greater than 0 or positive. If another statement and its converse are both true, like the example I gave at the beginning of today, if a triangle is equiangular, then it's equilateral, and conversely, if a triangle is equilateral, then it's equiangular, then we can consolidate those two statements and say a triangle is equilateral if and only if, so it goes both ways, if and only if it's equiangular. So if you have one, you have the other. So that's, again, called logical equivalence. So let me leave you with a couple of things to write down and try to prove concerning the idea of greater. So we have a notebook, very good. So suppose A, B, and C are, and we'll conclude with this, unless anyone wants to stay and ask specific questions, but we'll conclude the formal part with a couple of examples. So given that A, B, and C are 3 integers, 3 whole numbers, and given A is greater than B, okay, so that's given. Now, prove that if you add the same thing to both sides of an inequality, you preserve the inequality. That means you keep the inequality going in the same direction. So prove that if A is greater than B, then A plus C is greater than B plus C. Okay, so I've added C to both sides. Do the same thing if you subtract the same thing from both sides of an inequality. If A is greater than B, prove on the basis of the definition, if A is greater than B, then A minus B is greater than A minus C. So those two say that if you have an unbalanced scale and you add the same thing to both sides, it remains unbalanced in the same direction. And if you subtract the same thing from both sides, it remains unbalanced. Now let's look at multiplication. We won't do division because we're not doing division here. We'll have something called the division algorithm, but that is a statement about whole numbers, about integers. And we'll talk about on Thursday if A divides B, but that's not division. It still deals with whole numbers. So prove that if C is, now we need a separate proviso. Now, unlike in the first two examples where C could be any number, suppose C is a positive number, positive integer. Show, prove on the basis of the definition of greater than, that if A is greater than B, so that's the assumption for all these, A is greater than B, prove that if, in addition, C is greater than 0, is positive, then if you multiply both sides of an inequality, it's an inequality if one thing is different from, greater than, or less than another thing. If you have an inequality, you can multiply both sides of the inequality by the same positive number and preserve the inequality, keep the inequality going in the same direction. So prove that if C is a positive number, A times C is greater than B times C. So you're multiplying both sides of the inequality by the same positive number. A times C, show that that's greater than B times C. On the other hand, if C is a negative number, prove that multiplication of both sides of an inequality by the same negative number reverses the inequality, turns around the direction from being greater than to being less than. So prove that, again, A is greater than B, that's what we're starting with. Prove that if C is a negative number, then A times C is less than, turn the inequality around, less than B times C. So this time prove that if C is a negative number, then A times C is less than B times C. Also, suppose we have two inequalities in the same direction with all these numbers A, B, C, and D positive. Let A, B, C, and D be positive numbers. And let's conclude with this. If A is greater than B and C is greater than D, prove that A plus C, the sum of the two big ones, is bigger than B plus D, the sum of the two smaller ones. And that'll work in any case. But for multiplication, they all have to be positive. Prove that A times C, the product of the two bigger positive ones, is bigger than B times D, the product of the two smaller ones. So if A is more than B and C is more than D, prove that the product of the left sides, A times C, is bigger than the product of the right sides, B times D, where A, B, C, and D are all positive. So try writing that out, and by Thursday, I hope I'll be able to write to you. I'll need more guidance. So we will conclude the formal class meeting now, but if anyone wants to remain and ask some questions or complain about how difficult this is without being able to write it down, you can stay and do that. Okay, so I think I said on Thursday, as soon as I learn how, I will post the syllabus. There are a number of documents I want to put on Blackboard. I may actually even know how to do it because I have them in Dropbox, so I have to take them out of Dropbox and then attach them as an announcement to email to you. So yeah, I have a number of these things are prepared that I mentioned to you on Thursday. The curriculum, the state of policies and expectations, which includes a excerpt from the academic calendar. You all got my email that, wow, the university has finally decided. I've been trying to do this for the curriculum committee for like 30 years, and they didn't do this because of me. Even the school didn't do it because of me. The business school is always opposed to it. The business school didn't want to even have W's. They wanted you, once 3 weeks were over, you're trapped in the class. They relented and made it after 11 weeks, but that still wasn't satisfactory. So hey, they've made it up till the last day of classes to get out of the class with a W. So anyway, I have this document called Forms of Integers, a whole bunch of things for you to prove. Yeah, so all these things, this list of textbooks,